Yes, class, am I audible? Yes. Okay. Yes, Shaima, we are starting with a new chapter. We had completed motion in a vertical circle, Zainab, right? So motion in a vertical circle is over. So basically, the circular motion part which we were doing, which was the portion from your not only laws of motion, but from your circular motion also, from your rotational motion also, all these. All right. So this is basically this chapter is now we are going to start a new chapter. This chapter is work, energy, and power. So now which chapter is this? I think Shaima, I have taken out the friction portion also. You asked me in the last class, so that couldn't be discussed in the last class. So that I'll discuss with you. Whatever doubts you have, you all can ask. Okay. But let me just start with some portion of work, energy, and power. Or wait, let me discuss this one. Wait. Yeah. See, class. These were the questions, right? Which were sent. So a block of mass 2 kg is placed on the floor. Now mass is 2 kg is placed on the floor. Coefficient of static friction is 0.4. Right? If it is 0.4, frictional force which is applied is 2.5 Newton. Calculate the force of friction between the block and the floor. So this is, see, 2 kg is mass. This is mu. Normal reaction is there. Downwards we have mg. All right. So we have mg. We have normal reaction. So mass is present over here. So you know normal reaction is equal to mg. Our frictional force is equal to mu n. So frictional force is equal to mu mg. That's it. What you have to write. What all things, Shaima, am I audible or not? If my voice is cracking or something, please let me know. One thing I wanted to say, this portion, Shaima, only this question you have answered. What about the other questions? See, by answering a single question, at least try whatever things you can figure out from the question. You shouldn't leave the question blank like this, right? Only one question you have attended, Shaima. That's what I was saying in the last class. This is your paper. I wanted to show this to you so that whatever doubts you are having, it can be clarified.
Ma'am, I wanted you to explain the second and the third question.
Yes? See, okay, this question you wanted me to explain.
No, ma'am, the second and the third question.
Just tell me which one, Shaima.
Question 2 and 3.
Question 2. Determine the magnitude of frictional force and acceleration of the block in each of the following cases. See, we have to determine the magnitude of the frictional force and acceleration of the block in all of these. One case I'll discuss the rest of it. Okay, let me discuss all of these only. Okay. See, this is the force which is coming here, right? Downwards we have mg, which is present, right? And since this is in contact, this force which is coming away from the body. Remember one thing, whenever you have normal reaction, for normal reaction, always remember if this is my surface, right? And if anything is in contact with the surface, I'll always get it perpendicular like this. I'll always get this perpendicular. So if my rough surface is like this, right? So this will be the normal reaction. All right. So downwards is mg. Normal reaction is this. This is which force? This is the 100 Newton force which is acting. So it is basically stopping the body, right? Your block will fall down. So if the block falls down, what is the tendency of the body? tendency of the frictional force to act in a direction opposite to that. We have done this question, by the way, Shaima. This type of question we have already done. So just have a look there. So above force will be the frictional force. Why? See, look like this. If I have this, right, and I have this. If I leave, this has the tendency to go downwards, right? Right? This is the tendency. If a body is there which is present, it has a tendency to slide away and go down, right? So if the body has a tendency to slide away and go down, frictional force work is to stop the body, right? Now, if your body, suppose this is the surface, this is the wall, this is the object, this has a tendency to fall down. Frictional force always acts in the opposite direction. Friction has to stop the body from moving. Now, in this case, since the body is falling downwards, your frictional force will act upwards. Okay. Now, straight away, your frictional force is balancing mg, right? And your normal reaction is balancing the 100 Newton of force. So these are the four forces which we are having in both the directions. So look over here. Frictional force, mg, 100 Newton and normal reaction. Now we have mu k with us. Now we have mu s with us. Mu k we use to get acceleration part, kinetic friction, which is in motion part only. And mu s we have for the static friction. Now, what can we write? Our frictional forces mu n. This n is our frictional force, right? mg we'll use to get acceleration. Frictional force का formula क्या होता है? Mu n, right? The formula of the frictional force is simply mu n. Do not focus on this body which is coming downwards. Your focus is to just have the look where what is the normal reactions value. Here in this question, particularly it is saying normal reaction is balancing this 100 Newton. Basically, our normal reaction is equal to this 100 Newton. Let's say the gravitational force mg is equal to 5 into 10, which is equal to 50 Newton. This is the static frictional force, so this is our magnitude of frictional force, right? But when we are talking about acceleration, when will the acceleration come? Should we have kinetic friction or static friction? Voice is breaking. Wait, let me just change the internet. Just wait. I'll confirm again. Wait. Now just update me. If it breaks again, please just update me. Now see. So out of you all only tell me two forces you have. Static friction and kinetic friction. Now in the calculation of acceleration, which of these would we should use? Fk or Fs? Which one of these according to you? Yes, Shaima, answer.
Kinetic friction.
Kinetic, right? Kinetic one. Because now the body is in motion, right? The body has started moving. So our acceleration calculation, we have kinetic friction. Kinetic friction, if you calculate kinetic friction is 30 Newton. Now, how do we write? Body has the tendency to go downwards. So mg minus the force above. What is the force above? Above force is kinetic friction, which is 30. So kinetic friction is equal to, this is what? This is the net force. Downward force minus upward force, right? Force is going downwards, force is going upwards. Net force is mg minus f, right? Why mg minus f? Because acceleration will be downwards. Body has the tendency to go downwards. Acceleration will also act downwards, right? So mg minus fk is equal to, what is force equal to? Net force is equal to mass into acceleration. So this is mass into acceleration. Straight away you have the equation. So here we'll have mg is 50, Fk is 30, mass is 5a, right? So this is 20 is equal to 5a. So acceleration is equal to 4 meter per second. Like this you have to calculate. Now it's clear?
Yes, ma'am.
All right. Now let's discuss this work, energy, and power, right? I'll start with this. Now, work, energy, and power. It's a short chapter. Let me just give you a brief introduction about this chapter. It's a short chapter. It's easy to score because the best part about this chapter is that work, energy, and power, all these three quantities are scalar. All right. So when we have scalar quantities, the advantage that we get is we don't have to use our parallelogram law and all the vector laws. Straight away you can add, straight away you can subtract, right? So work, energy, and power. This is the name of our chapter. So we'll also be studying this into three parts. First part would be work. Work is very easy to understand. Just one or two formulas you have which you have to manipulate and use. So work part you will be able to do. Next is energy. Energy is the lengthiest part of it because though you have two types of energies, only kinetic energy and potential energy, but we have to do that in detail because only two energies are present. And last one is power. All right. Power is also a small portion. So let us not waste our time and start with the work part, right? At least we should be able to complete work in our today's class, right? Work, energy, and power. Work should be completed in today's class at least. All right, so let me start. So look in the screen. Look at the screen over here, this figure. This is the body of mass M. Now I have dragged the body. All right. So there is a certain displacement which is covered in the ground. A box was there. I have dragged it forward and kept it like this. All right. I have dragged it forward and kept it. So there was a force which was required to pull it. A force was required to pull it and mass was displaced from its original position to a new position. So initial position, final position, there's a displacement cover. Basically, dot product you have already studied. Work done is the dot product of force and displacement. Now, when we were studying dot product, I have told you that it is also known as the scalar product. Why scalar product? Because class, whenever we use dot product, both the quantities will be vector. See here, we have force, a vector quantity, we have displacement, a vector quantity. But the resultant work done, it's a scalar quantity, right? So force into displacement. Now, how do we expand this work done? This is equal to F S cos theta. This is how we have to use it. Force, displacement, and the angle which is made between the force and displacement. So it's a scalar quantity. What is the SI unit? SI unit is joules. We use joules. And CGS unit is erg. So there's a conversion also, which if you remember, we have done it in the dimensional analysis. So 1 joule is equal to 10 to the power 7 ergs. Write down this portion, then I'll discuss this. What is work done? Did you understand? Whatever is the amount of force required to displace a body, that is called as the work done. The amount of force which is required to displace a body. Write it till here. Any queries? Ask me. Write it till here first. Okay, see this question. It says that force acts on a body and it gets displaced by 5 meter. If the force acts at 60 degree to the displacement, you have to calculate the work. Easy and simple. You have to use the dot product. So work done is equal to F dot S, which is equal to F S cos theta. Force is 10, displacement is 5, cos 60 degree is half. So this is 25 June. That's our answer, right? Easy. Quickly write down this. All right. So in this question, we have force given in Cartesian form. So the previous question was based on the yes, Zainab, right. We have to do it in Cartesian method. Good. See, I cap, J cap, K cap come. That if they come, that is your Cartesian form. And if you have angle given, that is your polar. So this is the difference which you have to remember. So see, force is 2I cap plus 3J cap plus 5K cap. But before this, we have the barrier of the displacement, right? The initial point is 3 comma 2 comma 1. Second point is 2 comma 1 comma 1. Like this, it's mentioned. So this is X, Y, Z. This is X, Y, Z, right? So how do we write our RA? So this is written as 3I cap plus 2J cap plus 1Z means only K cap, right? RB, this is 2I cap plus J cap plus K cap, right? Now displacement we want. How can we calculate the displacement? Final minus initial, right? So here we'll have final minus initial. This is final is 2I cap minus 3I cap. So that means minus I cap, right? J cap minus 2J cap. That is minus J cap, right? K cap minus K cap, it's 0. So this is what we have right now, right? Minus I cap minus J cap. And this is our position vector displacement. And the force is 2I cap plus 3J cap plus 5K cap. Right? Now, when you are calculating the work done, straight away you will write work done is equal to F dot S. 2I cap plus 3J cap plus 5K cap, and displacement is minus I cap minus J cap. Now this you have to tell me. Quickly tell me the answer. Write it and quickly tell. Okay, Shaima's answer is 0. Zainab, your answer? See, I cap term gets multiplied with I cap term. 2 multiplied to minus 1, that's minus 2. 3 multiplied to minus 1, that's minus 3. So straight away it is minus 5, not 0. How 0 you are getting, Zainab? Shaima. K cap term would be 0 because there is no coefficient for K cap. Minus 2, minus 2. Okay, done? Or by the time you all are writing, write it. Start with this next question. You got minus 5, Zainab. Okay, good then. So I think it's done then. Let me start with the next question. Next question says that force is given as 3x square plus 2x. This is acting on the body. Displacement is given from 0 to 2. And we have to calculate the work. Now the problem is that our force is not constant. If I take x as 0, I'll get force as 0. If I take x as 1, so I'll get force as 5, right? So I'm having different values, right? 3x square plus 2x. If I put it as 2, so it will be 14. So values of the force is changing. It means it is variable force. So for variable force, this is the formula for work done. F dot dx integral from x1 to x2. So here the force is variable. And added somewhere, we use the formula work done is equal to F dot S only when our force is constant. All right. Now, simple integration, all of you know. Work done, yes. Force, I'll put it as 3x squared plus 2x. This term dx from 0 to 2. Let's separate the term 3x square dx from 0 to 2 plus 2x dx from 0 to 2. So this is 3x cubed by 3 from 0 to 2 plus this is 2x square by 2 from 0 to 3. 3 cancel, 2 2 cancel. We just have to put the upper limit first and then the lower limit. So this is 2 cube minus 0 cube plus this is 2 square minus 0 square. So this is 8 plus 4. This is 12 joules. Okay. Write it down. Then we'll see the graphical method. How did how did we x cube this x cube? Integrations rule. X to the power n becomes x to the power n plus 1 divided by n plus 1. So this is x square. So x to the power 2 plus 1 divided by 2 plus 1. So this is x to the power 3 divided by 3. This All right, done. Now we have the graphical method. So we have done the formula part. Now we are left with the graphical method. So if you have a graph, how do we solve the graph while calculating the area or for calculating the work done, not the area? Area is actually, see, I'll tell you one thing. If two quantities are present and you're getting the third quantity while multiplying it, or if I say, let's say distance, speed into time will give us the distance, right? Speed into time will give us the distance if this is the case. So what we'll do, speed into time is equal to the distance, right? So distance, we write speed is equal to distance upon time, right? Now two formula we have from the same one. Speed is equal to distance upon time. Speed multiplied to time is equal to distance. So two cases we have. We, in the first one, we are multiplying two quantities. Speed into time is giving us the distance. And in the second one, we have distance getting divided by time, right? Which is giving us the velocity. So if I have to find out position through VT graph, I will find out the area. And if I have two quantities which are getting divided, right? If two quantities, these are getting divided. So what we will do, if these two quantities are getting divided, we will straight away find out the slope. That is the thing which you have to remember. So we will be calculating the slope. That is the rule which you have to remember. So area above the displacement axis, always take it as positive, and whatever area is below the axis, take it as negative. So in our formula, work done is equal to force multiplied to displacement. So that's why area under the graph will give us the will give us the work. Write down this part, then I'll discuss how to solve it. Okay, write it.
Ma'am, can you scroll up?
Ma'am, can you scroll up?
Ma'am, can you scroll down?
All right, yes. Now see, you have to calculate the work done here. So force is given on one axis and we have the displacement on the other axis, right? Now see, this work done, one thing remember, whatever area is there above the principal axis, that is taken as positive. And whichever area is below the principal axis, that is taken as negative, right? So this one will be positive, this one will be negative. Now, what is the area of a rectangle? It's a simple rectangle. This is 2 meters, this is 3 meters. So when we are calculating area of the rectangle, it is, or firstly, our work done is actually area of the rectangle plus area of the triangle. So once we are calculating this, area of the rectangle is simply 3 into 2, right? But since this is negative, we will put plus. This is half, base is 2, height is also 2. Yeah, this will be minus, right? So 3 into 2 is 6 minus 2. This is equal to 4. This is the answer. Write it down. That completes the work done. All the questions which are possible, we have done. Now we'll start with energies. And then you will see how the concepts of work done will come here. Write it, take a break of 5 minutes, then I'll start with energy. All the concepts of work done which are present other than what we've studied will come under mechanical energy. Okay, start writing this. Take a break of 2 to 3 minutes. I'll start with energy. Okay, let us start with this now. Energy. Now, mechanical energy is basically of two types, which we have to study. One is our kinetic energy, other is the potential energy. So kinetic energy plus the potential energy will give us the mechanical energy. So basically, mechanical energy is a general term for the combination of kinetic and potential energy. Okay, class. So when we are using the term kinetic energy or potential energy, these are separate energies. But if I'm using the term mechanical energy, that doesn't mean that it's a new type of energy. It's basically combination of the kinetic plus the potential. All right. So this should be there in your mind because many a times a question is asked where you have to calculate the mechanical energy. So in those cases, first you have to calculate the kinetic energy, then you have to calculate the potential energy and take out their sum. You cannot leave it at one step, right? So for that, you can write it, not right now, once I'll give you time. Mechanical energy is basically the kinetic energy plus the potential energy. So this is not a new term. Mechanical energy is kinetic and potential energy. So what we'll do, we'll go one by one. Now see, I have to, work done's concept is over like this. So see, concept of work done is not over as in concept of work done in terms of variable force and the constant force. These are over. All right, class, this is over in terms of this. Now, if we are having kinetic energy or potential energy, there also we'll be having the concepts of work done. And if we have the concepts of work done over here, then that is going to get added in the energy portion. That's why I'm saying work done is over. We have to focus on the energy. So first, let us complete the kinetic energy. I don't think so. Potential energy will be started in today's class. Even kinetic energy will not be completed in today's class, but let us at least start with this. One thing which you have to remember before we start with anything is the work energy theorem. All right, work energy and theorem. So what is the work energy theorem? Work energy theorem basically says that whatever is the net work done we are getting, net work done is actually the change in kinetic energy. So total work done is the change in kinetic energy. So you can say work done is equal to the change in kinetic energy. So see, we have already studied two formula for work done. One was F dot S simply. Second one was F dot ds, right? This is what we had studied. So F dot S and F dot ds, both of these we have studied. Now a third one has been added to your formula list, which is work done is equal to change in kinetic energy. Now, what is this kinetic energy? I'm using the term kinetic energy and I have used it a lot of time by now. What exactly is this kinetic energy? Basically, any movement is there by the body. The body covers a certain distance. Body has a certain velocity with which it was moving. Or simply you can say motion of the body has occurred. Body has moved from one point to another, right? So this energy we say this is called as the kinetic energy, which is there due to change in the position. Just remember, kinetic energy comes into action whenever there is a change in position. Body moves from one point to another. A person has started moving, right? He is going from his home towards the office, right? So when the person has started moving, or even as soon as he got up to stand, from sit to stand, kinetic energy's work has started. Now, when the person has started moving, kinetic energy is increasing. So whatever changes will be there, that those changes will be there in the kinetic energy itself. So what exactly is kinetic energy? Kinetic energy is basically the energy possessed by a body due to its motion. All right, whatever is the change, motion occurred in the body, means velocity was there, initial velocity was there, final velocity was there, a change has occurred in the body, or like that. So kinetic energy is equal to half mv square. This is the formula of kinetic energy. It is half mv square. This is a very, very important formula, and we remember half mv square as the unique formula for kinetic energy. You do not have a similar formula for a different energy or kinetic energy. Half mv square is very unique. Whenever you see half mv square, immediately kinetic energy should come to your mind. All right. So that's why half mv square, make a star point, write a star around it whenever you are copying it. You should remember that you have to remember this formula at any cost. Without remembering this formula, you will not be able to solve the entire chapter, upcoming chapters till your class 12. This is just your 11th class. Even in your class 12, you'll not be able to solve it. How do you think these all the things which you're studying in 11th affect your class 12? Suppose you have electrostatics in your class 12. An electron is moving. If an electron is moving around the nucleus, there is kinetic energy in the electron, right? Now in your 12th standard, again, the kinetic energies concept has come, which was there in your class 11th. So now your kinetic energies concept has been used. So it means you have, this is such a type of concept which is not only limited to this chapter or limited to your class 12. This is one such portion which will be continued to your class 12, and it's a portion which you should remember, like your additions and subtractions, like vectors. I have told you vectors will be coming in your 12th class, and you see in every chapter apart from vectors have been coming, right? So kinetic energy and potential energy are very important, but potential energy has a little different concept. That's why I'm not focusing on potential energy right now. Potential energy is a very elaborated concept which requires a little knowledge about the basic forces that we will be doing later on. Kinetic energy has no such boundaries. There is a change in the motion, you have the kinetic energy, which is half mv squared. So this part is clear to both of you? Yes or no?
Yes, ma'am.
Okay, good. Now see, let me just start with this portion. Basically, a sort of derivation which we have for the kinetic energy. Mass m is present, mass m is moving from one point to another, and initial velocity is v1, final velocity is v2, acceleration is a. Now, f dot dx we'll write. Now you know f is equal to ma. So straight away I'll be writing ma over here. Straight away we'll use ma. See, we know f is equal to this ma. So we'll substitute this here. All right, we'll put it here. So this is equal to, from x1 to x2, ma dot dx, right? Now acceleration is also something which we know. Acceleration is dv over dt, correct? Acceleration is simply dv over dt. Now, here we'll put m into dv over dt dot dx from x1 to x2. Class dx over dt. What is this? This is again the velocity. So we have m, v, this v, dv. These three terms we have, right? So how do we arrange it? Integral of mv dv from x1 to x2. Now see, x1 and x2 we cannot write now. So we are replacing it with velocities. See, if your displacement is changed, your velocity will also be changed. Why are we not solving? Because this is mathematically incorrect. M dv over dt you cannot write. You have to write it as m v dv over dt. So we are integrating it from v1 to v2. So if you are integrating it from V1 to V2, we'll be using dV also over here. So if we use dV, V1 to V2, so see what will be the simplest of the derivation. Simply this is V to the power 1, so it becomes square divided by 2 from V1 to V2, and this M is already present, right? So this is equal to MV2 square, or this is basically V2 square minus V1 square, M by 2. So multiply this M by 2 with both of them, you get half MV2 square minus half MV1 square, right? So this work done gets stored in the form of kinetic energy. And what is kinetic energy equal to now? If this is getting stored in the form of kinetic energy, half mv2 square, half mv2 means the final kinetic energy, minus half mv1 square. V1 means the half mv1 means the initial kinetic energy. So final kinetic energy minus initial kinetic energy is what? It's basically the change in kinetic energy. And that is only equal to the work done. This is what we call as the work energy theorem. And this is the derivation for the same. This is the work energy theorem. So in work energy theorem, you have to remember this. This is important. And this is the derivation. All right. Write it down. Any queries, please feel free to ask and get it clarified. Start writing from here. Next topic as your mechanical energy.
Ma'am, can you scroll down? Ma'am, can you scroll up? Ma'am, can you scroll down? Ma'am, can you scroll down?
Please text me done once completed. Okay, then if completed, you can leave. Tomorrow we'll complete this portion of kinetic energy. Okay, thank you so much. Please revise and come.
Thank you, ma'am. Bye.